to a new topic. The remaining topics in this course are going to be overviews of different aspects of substations. One of the first things we're going to handle is high voltage DC. Oh, and also I walked by Professor Pozega's class and I saw that she was doing op amps, right? Oh, but that was a different class. Okay, never mind. 280, not the same as 180. Okay. We were talking about solid state relays in 180, and op amps are part of solid state relays. So, okay, so today's the 2nd of March. So HVDC stands for high voltage Do I have to spell it DC, direct current? Okay. Fax is flexible AC transmission. Both use power electronics. Okay. So we couldn't have those a long time ago. Okay. So let's start with high voltage DC. First use in Sweden. Okay, so they had the Swedish mainland, and then they had an island. And they wanted to get power from the mainland to the island. Oh, gotta throw out that pen. Okay, so that's what they wanted to do. Okay. Before this, they would have had to use a small generator on the island. I think this is about approximately 19 miles. Okay. So, the people on the island wanted power, reliable power, and people on the mainland had power, but no way to get out there. So we could have an AC line. It's obviously not going to be above ground, right? It's an underwater cable. Okay. So that underwater cable has inductance, resistance, but it also has capacitance. Okay. So we'd have so much of the current coming in, going through the cable, that it's not realistic. We can't use cable for this long a distance. Does that make sense? Okay. So this is Gotland, Sweden, and they were going to try a high voltage DC cable, right? Only charge up the capacitance once. Okay. So the first time you energize a cable, it's going to draw a lot of current into the capacitor, but then after the voltage is on the cable, what happens to that current? It goes away, right? With an AC system, we're going to have to keep charging and discharging those capacitors. With a DC system, it's only going to charge once. Okay. There. Okay. So we've got three-phase going in. Okay. And then on the output of this, we have plus and minus. Okay. Now, these are the symbol for a diode. Those mercury arc valves, you can turn on and off. So this is a diode. And this would be the mercury arc valve. So this gate so when a diode has a positive voltage across it, what happens to the diode? It turns on, right? With the mercury arc valve, we can control when that diode turned on. Okay?
What's the point of a diode? What does it do?
What?
What does a diode do?
Okay, so we've got three-phase AC going in. Okay, and if we take each one of the phases, I didn't draw that perfect, but basically let's say that this guy right here was this is going to be VA, and this is going to be VB. So with just a diode, when we hit this point right here, VB is going to be more positive, so we'll turn on the diode for VB. Does that make sense? So the DC that we get out is going to be like that. Have you had a full wave rectifier yet? Have you seen a full wave rectifier yet? No? Okay. So let me draw a full wave rectifier. Instead of doing okay, so. Okay. So, V plus, this would be minus, this is VDC. And typically what we would do is we'd have a transformer. Let me go here. Okay, so we've got those two connection points. And I'll put a resistor right here. Okay, so this is AC, diodes and DC. And so our AC waveform is a lot simpler to draw. Three, two, three, there we go. Okay. So, with a positive voltage, okay. So, how do we want to number these? How about 1, 2, 3, 4? Got 4 diodes. Is that okay? Okay. So in the positive half of the cycle, which one of these 2 diodes is going to be turned on? 1, right? Okay. So we have the positive voltage here, and then 4 is going to be turned on. Okay. So right here, 1 and 4. Okay. What's going to happen when that voltage goes negative? So this is a negative right here. Well, this voltage here, even if it's 0, if we've got a negative voltage there, what's going to happen to this diode? It's going to turn on, right? And so is this diode 3. Okay. So there, we're going to have 2 and 3 turn on. And what's going to happen when 2 and 3 turn on? Well, 2 and 3, this is the negative side of the AC waveform, right? Okay. So 2, we're going to get the inverse. If we have 2 and 3 turned on, we're going to have the inverse of that waveform. We're flipping the waveform, right? So this voltage here, that's V load. And V load is also this voltage right here. Okay. So we're taking the AC voltage, and with 4 diodes, we can make it so that it never goes negative. Okay? So that's called a full wave rectifier. So the diode is going to turn on when there's a positive voltage across it. So on the positive half cycle, 1 and 4 turn on. On the negative half cycle, 2 and 3 turn on. But what that does is it inverts the voltage across the load. Okay. Okay, I'm doing the same thing here, but with 6 diodes. So whatever voltage is more positive, that's the voltage that's going to turn on. Okay. And that's what this DC link does. Okay. Any questions on that? Okay, so that was the Pacific high voltage DC line. So that went from Los Angeles to Oregon. I spell it Oregon.
Oregon?
Yeah.
G-O-N?
G-O-N?
Yep.
Okay. Okay. So I'm blanking right now on what the voltage was for the Gauntlet system, but I worked on the high voltage DC line in Los Angeles. Oregon was a Grand Coulee Dam. Grand Coulee Dam. And that first started up, it was 400 kV, plus or minus 400 kV. So it had 2 conductors, a plus conductor and a minus conductor. Okay. So this was plus 400 kV. This is minus 400 kV. So the total voltage was 800 kV times 1,000 amps. So what is that going to equal? 800 megawatts. Okay. So you have these things on both ends. So you've got the converter stations on both ends that you have to pay for. Okay. You convert that AC to DC, and then down in Los Angeles, they convert it back. When they first put this in, the idea was that they were going to share power. Los Angeles would give power to Oregon in the wintertime. In the summertime, Oregon would give power to Los Angeles. Okay. It just so happened that after they put this in, it was a real rainy season up in the Oregon area, and so they were producing power all year round. Okay, and so Los Angeles ended up getting all the power, and they never had to send anything back up to Oregon. Okay. It was approximately 500 kilometers. Um, when you're looking at AC line, you've got 3 wires. So you got to pay for the 3 wires. You got to pay for wide towers. You only have 2 conductors. Plus or minus, and smaller towers. Okay, so right about 300 kilometers. Oh, and this cost right here is the converter station. Okay. So the reason why they put up high voltage DC, it's cheaper because the lines only have to hold up 2 wires or 2 phases, right? AC has to hold up 3. Okay. So you can save money by going to DC, realizing that you have to pay for these inverter stations. You have to rectify it to DC, and then you have to invert it back to AC. Okay. So you get that problem. So that was that thing. You also had problems Oh, yeah, yeah. So there was already a transmission line from San Francisco to Los Angeles. Had stability problems. That was a 500 kV line. And then we had problems with loop flow. So, if we go over loop flow, we've got San Francisco up here. We got LA down here. We've got that transmission line there, right? Let's say we're having power going there. We had LV, is that okay for Las Vegas? Okay. Actually, I should include Idaho in here somewhere too. It actually went all the way up to Idaho and back around. Okay. So with AC on an interconnected grid, we had power that was being sent down from San Francisco, okay? So we wanted this one, so that's good. That's okay, and this was bad. Okay? It's just, we want power flow from San Francisco to Los Angeles. Las Vegas wanted some of the power from Los Angeles. Los Angeles needed power, but they were okay with losing some of that power. But then the AC grid through Idaho actually was making a completed circuit, and the current would flow around that loop, okay? So we had problems with AC. Stability problems, that means if they lose the line, San Francisco goes black, Los Angeles goes black, that's a stability problem. Loop flow is, because this thing is interconnected, you have a current path, and that current is just going around in circles, okay? So, like I said, we wanted to go from San Francisco to Los Angeles. We were okay with some of the power flowing back there to Las Vegas, but then when the path was completed, it's bad. So DC, converting to DC, okay, took care of that loop flow. Okay. Okay. So the first upgrade was to go from 400 kV DC to 500 kV DC. The second one was to go from 1600 amps to 3100 amps. So how much can the Pacific High Voltage DC line now provide for Los Angeles? Well, plus minus 500 kV equals 1 mega million volts. So that means 3.1 gigawatts. The total load of Los Angeles is about 7 gigawatts. So half the power, a little less than half the power for Los Angeles is coming from the Pacific HVDC line. How do you spell Phoenix?
There's an E after the O.
Phonioenix? No, it wasn't from Phoenix. From Phoenix, they added a high voltage AC line. Okay, so in the late 60s, they had 400 kV DC. In the middle 70s, they upgraded that to 500. Okay. When they upgraded this, they went from 1,000 to 1,600. And then in 87, I was there for the beginning of it. We basically tore down the converter station on one side of the freeway and put a new one on the other side of the freeway, bumped the current up to 3,100 amps at plus and minus 500 kV. That's 3.1 gigawatts. We added a high voltage AC line, 500 kV, from Marketplace substation near Phoenix to Adelanto near LA. And then we also added the Intermountain Power Project from Delta, Utah. And this was basically a coal-fired plant that we built out in the middle of the desert and then shipped that power to Los Angeles, 2.2 gigawatts. So we can see here 5.3 gigawatts of the 7 gigawatts needed for Los Angeles is provided by high voltage DC. Okay. So that's in America, that's the biggest ones. We also have from SD and ND to Minnesota. So basically in the Dakotas, okay, so we took, they have coal mines out there. We put a power plant right at the mouth of the coal mine. Okay, so from North Dakota, we've got a DC line that goes into Minneapolis. And from South Dakota, we've got a line that goes up to Duluth. It doesn't look right for Duluth. I don't ever forget.
Duluth is pretty north.
What?
We were talking about, yeah, Duluth is north. Duluth is north of Minneapolis.
Yeah, but I thought I spelled Duluth wrong.
Oh, yeah, you missed a U. After the L.
Oh, there's another U after the L? Oh, wow.
There you go.
Like that?
Mhm.
Okay. So this was Northern States Power. And Rural Electric Utilities. And Duluth was Minnesota Power. So as far as high voltage DC over long distances, those are the links that we have in the United States. Okay. Oh. I forgot the one near Boston. So we get Canadian Power from, this is Hudson Bay. Hydro. Hydro. There you go. So Hudson Bay Hydro, basically the native people up there put in a lot of dams, and we send the power to Boston. We got 3 islands off of Italy that we share power with. Okay. How do you spell destroyed? D-E-S.
Y-E-D.
What?
Y-E-D.
Y-D?
E-D.
E-D. Okay, so we also have links in between Norway, Sweden, Finland, Germany, and Denmark. Those are underwater. Okay, so I think I've covered all the there's probably some in China, but I don't know. I'm not going to go be exhaustive here. So Pacific HD, high voltage DC line. We got the two in Minnesota coming from North Dakota and South Dakota. We've got a line coming from Hudson Bay Hydros into Boston. You've got 3 islands off of Italy that are interconnected with DC. We used to have a high voltage DC line that went through the middle of Africa, but that got destroyed by war. And then we had high voltage DC in India. They set up the controls such that they didn't want to de-energize the line because they had people knocking on the towers to steal the line for scrap metal. So they kept the line energized. That tended, that caused a problem with the valve hull and basically destroyed one of the converter stations. We've got 10 links, over 10 links now, between Norway, Sweden, Finland, Germany. The interesting thing about that is that they just put one wire and then they're using the sea as a return path. Okay. So the high voltage DC in Los Angeles, we did the same thing, but the environmentalists didn't like that. We actually ran a line out to Malibu, and then like 19 miles offshore or 10 miles offshore, whatever it is, we had a huge wire cage. Okay, and then the Grand Coulee Dam is on the Columbia River, and so that was the return path. So if we lost one of either the plus line or the minus line, we could still ship power. We just had to go through use water as the return path. Does that make sense? And again, they limit how much we can do that. And it would be good to scuba dive near that sea electrode when it's in use. Okay. But it's a fun job to have to go out there and check the sea electrode because it's right there on Malibu Beach. So, you can spend all day going out there. Okay. In the little bit of time that's left, now, back to back it's not for great distances, but if you look at the Lower Peninsula and the Upper Peninsula is closely tied to Wisconsin, right? And so the phase angle on the power grid is similar to that of Wisconsin. Lower Peninsula is at a different angle. So if we want to ship power back and forth, we have to use a high voltage DC link. So there's a high voltage DC link near St. Ignace. okay? So you got AC cables going across the Strait of Mackinac, converting it back into to DC, and then right back again to AC, because it's two different phase angles on the voltage, okay? Got a whole bunch of back-to-backs between the east and west connection. So if you go through Kansas, over by Santa Fe, San Antonio, that's going into the Texas interconnection. Wherever you have, these two great systems coming in close contact with each other, you can't send power from one system to the other, so you have to convert it to DC and then convert back. Okay? Boy, I gave you a whole bunch of stuff on high voltage DC. This used to be my life I worked for Los Angeles Department of Water and Power for 8 years and Northern States Power for 6 years. So I used to do a lot of stuff with high voltage DC. It's neat stuff. It's being used all over the world. This is probably a little dated as far as the information goes. There's probably more plants out there, but it's a neat thing. Like I said, for long transmission, over about 300 kilometers, it's cheaper to go DC. For underwater, it's basically your only option because an underwater cable. Oh, there's also a high voltage DC link, 2,000 megawatts between France and England. You know, the English Channel there? Before they had the tunnel that goes underneath there, right? They had a high voltage DC link for many years. Now I think that high voltage DC link is in the tunnel. Is that what they call it? So they moved that. But yeah, again, that's a long distance, like 27 miles for the power line. I'll come up with a homework assignment on high voltage DC. I don't know if we need to do facts. I like high voltage DC, and that's in the textbook too. So, okay.